Thank you very much. Hello, everybody. My name is Jiansheng. I'm from Nanjing University of Post and Telecommunications. And my title is Precise Modeling and Interpretation of Bioactivities of Ligands targeting GPCR. And G protein coupled receptor, I think, is a class of protein, transmembrane protein family. Okay. There are two domains. The outside domain is for ligand binding, and the inside domain is for binding to G proteins. And the GPCR is very important for drug discovery. And the GPCR occupy about 33% of target of drugs. And as we know, drug discovery is a very long-term period, and include multiple stages. And artificial intelligence have been applied in most stages. My work is focused on screening this field. And the screening for hits, there are two ways. The first one is use the high throughput screening assays. And the assay uses some high throughput screening machine and computational chemistry to, but I think this is very time and labor intensive. And the most serious is they are not available for all components and target, especially for GPCR. And the visual screening, I think, is a very important complement for assay. And this is based on computational method. Can be divided to classes. And the first one, when you know the three-dimensional structure of target, you can use the structure-based method. And the most popular is the docking, protein ligand docking. When you don't know the 3D structure of target, you can use the ligand-based method. And the most popular approach are based on the machine learning. And my work is focused on this one. And now, machine learning has been widely used in ligand-based visual screening. And the typical application is based on the traditional machine learning method, such as neural network and SVM, decision tree. And now deep learning, I think, is very popular and have been greatly successful in ligand-based visual screening, and there are many works in this field. And multitask learning is also being successfully applied in this field. And the motivation of my work have 3 parts. The first one is accurate prediction of the ligand bioactivities. Okay. And this is very important. And there's an important challenge in this work. The most famous one is this and organized by the Merck company in the cargo. And many teams attend this challenge. Okay. And the deep learning wins this challenge. The similar challenge is also organized in China, in 2013, and most teams attend this challenge. So, but I think the accurate prediction is important. But I think comprehensive interpretation of the predictor, I think, is more important, because you can now understand the models and can help the scientists to optimize the leads in drug discovery. The third one is because I think this research has a huge commercial profit. So there's a lack of the open source code and data set. So I want to design and release open source code and data set in this work. This is my method, the PubMap method. The method contains 3 parts. The first one is to generation of ECFP fingerprint. The second one is feature selection, and the third one is the building of the models. I think ECFP is the very powerful and very popular fingerprint for drugs. And you can use different diameter to generate many substructures and identify and you can use the hash function to generate a binary representation. And each dimension of the vector represent one of the substructures. And in my work, I used the long extension ECCB. There are 2 reasons. The first one, if you want to get the excellent performance, I think use the long ECCB is a good choice, because there are more substructure to represent the components. The second one is it can reduce the occurrence of bit collision. And use the long ECCB, each dimension can precisely denote one specific substructure. So, but I think it helpful to determine more accurate substructure of each bit. But use the long ECCB, I think is very computational expensive, because and the serious program is it will lead to the case of dimensions, because the size of the future dimension ECCB is much larger than the size of samples. So it will heavily reduce the model performance. So I use the sparse screen method to heavily reduce the dimension of futures. The key idea is to delete the dimension with the 0 contribution to model. So By sparse screening, we can obtain a much reduced matrix, data matrix. Yeah. So get this data matrix, we can use the standard lasso to do feature selection. And then we can use the deep neural network to construct a model. Okay. And this is the data set. Okay. We use the 16 GPCR data set. Okay. And the data set covers most of the class of subfamily of GPCR. And the size of samples is from 300 to 4,000. Okay. And this GPCR data set has a significant cognitional significance. Okay. This is the model performance. And we can see that I used this side as the baseline method, okay? And we compared the method with the top 3 features selected from various sides. And then this one, from this, we can see that our method is enhanced performance, okay? If long ECCB are used, the performance can be further improved, like this one and this one, okay? This is the size of ECCB, right? And this is the baseline, okay? The second one is we divide the GPCR to 2 groups, and the second one is more ligands, and the second group has less ligands. Okay, we found that in group 2, okay, I think our method improved the baseline predictor. Okay, get more improvement in R² and RMSE. And this is the best line, and this is the best model. Yeah, for this one you can see that. Okay, and okay, it's more improvement. And we also consider the importance of the number of ligand samples on the model performance. And the model get more improvement on performance in group 2 and then group 1. And this is the effect of models on performance. We consider 4 cutoff models. This is DNN we used, and with the random forest and GBDT and SVR. And the DN is the best. And and we also consider the dependence of performance on the number of selected features. Okay, we consider 4 types, and this is the default, and we used and compare with this one. I think. The top 300 is the best, okay. And we consider the Pearson correlation analysis of select features, okay. The T is the top features we selected, and R is the random selected from a dimension, okay. And the last shows that the PCC, but all features are significantly higher than the random select features. It shows that our method is effective. And we showed the results. Yeah, okay. We showed the substructures selected by method. Okay. I think we chose this one, the S1PR5 GPCR as the data set. And this is very important GPCR. Okay. And we use this, use long SFP. Okay. And our model get excellent improvement. And this is the top substructures along with the PCC. I think this one, the top structures, I think is very important to the interpretation of the models. Okay, sure. And for the construction new and better ligand model, molecular. And this is the top 15 to 300 subjects. And list our source code and data set of models in here. And you can also download from the GitHub. I think conclusion is we can use the long ECFP and the sparse screening and to get a precise modeling and interpretation and for bioactives or ligands. But I think the more important thing is we model is a general random framework. It easily can be used in many fields, yeah, related, okay, similar work field. I can for the small drug discovery and maybe some material design. Okay, I think it's general. I think this is the person I want to thank to. Okay, we also thank to NSFC and NSF for the supporting. Okay, thank you.
Thank you. Maybe I can ask one. I didn't really get how you get this, how you achieve sparsity. Could you explain that again? Do you use a penalty that encourages sparsity, or what is the mechanism?
Okay. You say this one?
Yes.
Okay. I think that this is the sparse screening algorithm. Okay. This one. I think the key idea is to delete the dimension of has zero contribution to the models. This algorithm is very complicated, and maybe if you're interested, you can download, find the paper in NIPS 2030 and from Arizona State University, year lab. They got so many papers and good papers in this method, this algorithm. Yeah. Okay.
Okay. Thank you. More questions? Yeah. Could you go to the microphone?
So how long radius of you use ECFP? So ECFP
Adikit.
I mean how
diameter.
Diameter, yeah.
Diameter is 6.
6, and the fixed length speed. How long fixed length speed?
And many. Okay, you can. Okay, you can just one. Okay.
There are some memory issue when you use deep learning, because when I used ECFP, I said more than 10,000. Maybe there is too many memory issues, so I cannot handle it. My machine cannot handle it.
Yeah. This is the main contribution of my papers. Yeah. Okay. Because the dimension is very large, and it's much larger than the size of samples. So you must do do this one first, okay, and get a small data sample, data matrix with a smaller dimension of the features, so you can use a standard lasso to deal with and build the models.
Okay, so there is. Thank you again.
Thank you.
Jiansheng, for your talk.
Thank you very much.